ஐன்ஸ்டீன் அவர்களுடைய பொதுச்சார்பியல் கோட்பாடு மானிடத்தின் முன்னால் வைத்துள்ள சவால்களை முழுமையாக இல்லை என்றாலும் ஏதோ ஒரு பகுதி அளவிற்கு அதற்கு பதில் உரைக்க முற்பட்டவர் தான் ஸ்டீஃபன் ஹாக்கிங். உங்களுக்கு தெரியும், அவருடைய மூளை ஒன்றை தவிர கிட்டத்தட்ட அவருடைய உடல் செயலிழந்து தான் இருந்தது. அவருடைய முகத்தில் இருக்கின்ற ஒரு சிறு கன்னத்து அசைவு ஒன்று மட்டும்தான், அதன் மூலம் மட்டும்தான் அவர் இந்த உலகோடு உரையாட முடியும். அதனை வைத்துக்கொண்டு ஐன்ஸ்டீன் விட்டு சென்ற கேள்விகளை இந்த மானிடம் புரிந்து கொள்வதற்கு, ஐன்ஸ்டீனை தாண்டி இந்த மானிடம் செல்வதற்கு தன்னுடைய உழைப்பின் மூலம், தன்னுடைய சிந்தனையின் மூலம் நமக்கு வழிகாட்டியவர் தான் ஸ்டீஃபன் ஹாக்கிங். அந்த ஸ்டீஃபன் ஹாக்கிங் எங்கு ஆரம்பித்து எங்கு முடித்தார் என்பதனை ஒரு சிறிய அளவில் அறிமுகம் செய்யும் முறையாக டிஆர்ஜி அவர்களுடைய டாக்டர் டிஆர்ஜி அவர்களுடைய உரை இருக்க போகின்றது. டாக்டர் டிஆர்ஜி அவர்கள். அதற்கு முன்பாக டாக்டர் வி முருகன் அவர்களுக்கு டாக்டர் டிஆர்ஜி அவர்கள் இந்த சிறிய நினைவு பரிசை வழங்குவார். டாக்டர் டிஆர்ஜி.
நன்றி, தேங்க்ஸ். அவரை மாதிரி ரொம்ப தமிழில் பேச மாட்டேன்னா, நான் நிறையா இங்கிலீஷில் தான் பேச போகிறேன். ஏன்னா இந்த சப்ஜெக்ட் எடுத்துட்ட சப்ஜெக்ட் வந்து அந்த மாதிரி சூழ்நிலை. அதை படித்தது புரிந்து கொண்டது எல்லாமே இங்கிலீஷில் தான். அதனால் பேசுகிறச்சு அந்த இதை வந்து தயவுசெய்து மன்னித்துக்கணும். அந்த இதை ஆரம்பிக்கிறதுக்கு முன்னாடி சில விஷயங்களை சொல்லணும். ஒன்று, நான் வந்து I have met Stephen Hawking. He came to Bombay. Very interestingly, there was a meeting in 2001 in Bombay Tata Institute of Fundamental Research. And of course, I was working on string theory, gravity, some of those issues. And I went for the conference, and the greatest attraction at that time, star attraction, was Hawking. And of course, he came there, and he became immediately a celebrity in Bombay. So in the TIFR, Tata Institute of Fundamental Research, when we were all having lunch in the open air area, I actually had a small discussion with him at that time. First, my intention was to find out how he answers the questions. So I asked him some questions. And in those days, you remember 2001, you have not even heard of cell phones at that time like the way we do. And of course, he had a small computer, and he was in the wheelchair. And when I asked the question, there is a sentence: the black holes do not exist. Let us say that is the sentence. Then he types T. First word is the. So he types T. Most of the time, the computer will give some 3 or 4 choices. The, that, this, various things. So immediately the will come, so he chooses that. The next is black B, and then there are some more choices. First choice may or may not be correct, so he goes to the next letter, and immediately the choices are limited, and you will wonder, if you give any word, if you say what are the first 3 letters, most of the time you have very limited choice, 3 or 4 choices or 5 choices, which you see even in your WhatsApp. It gives you 3 choices. Most of the time it is correct. Some of them it goes to wrong message also. So this is what is happening, and he is constructing the sentence within 30 seconds. Whatever question you ask, 30 seconds is required for him, and he was doing it with his hand, finger. Okay, and that was, he had this autoneuronal disease, which I will mention here, by which the whole of his body is not working. At that time, his hand was working, and of course his head was working, brain was working, and this is the way it went on. And he answered all the questions within 30 seconds, and then presses the button, and there is a metallic voice. The metallic voice says, the black hole doesn't exist. This is the way it will go on, and then it will go on to the next question, etc. Very interesting. And I happened to meet him again in 2011. Okay? In 2011, 10 years later, even his hand was not working. His hand was not working. The only part which was working was above his mouth. This place is eyes. So he was constructing the words, sentences by his eyelash, by looking and imagining some words and then click like that and then constructs a sentence. I did ask him questions at that time also. That was in United States when I was visiting American Physical Society meeting, and this is the way he answered. I said, hats off, what is this? What great physics he has done with such a difficulty in his life, and that is unimaginable. You will understand this when you see some of the things. I have some video clips from actual speech which he has given, and also some part of a trailer of a movie. So I will also show those things also. My previous speaker gave a nice introduction to one aspect, which is general theory of relativity, space-time. So Newton, what he said was, anything will go in a straight line unless acted on by a force, which is very simple. Unless acted on by a force, you take a carom board, you take a coin and then hit it, it will go in a straight line. You know that it will go in a straight line. Well, if you want to throw a cricket ball, if you want to make it curved, you have to give a spin, and also there should be some atmosphere where water vapor is there. Nowadays, even football, people kick from a corner and that ball comes in a round like this and then goes into which is very difficult, extremely difficult. By practice, people are doing that. So the Newton's first law says everything will go in a straight line. Then you can ask the question, why is it Earth is not going in a straight line around, say, Sun? Why is it not doing? So it is acted on by a force. So there is a gravitational force which was there, and the greatest contribution of Newton was there is some universality about it. What is universality about it? The force with which an apple falls here and the force with which Earth is pulled by the Sun, they are one and the same. There is no thing. It only depends on the masses there and the distance between them. It doesn't matter. Anything beyond that is irrelevant. There used to be a joke. Of course, people say Newton discovered the law of gravity, which is universal law of gravity, which is true. And one of my friend who is no more, who has made fantastic contribution in the same black hole theory, which we are talking about, his name is Vishweshram. He is from Bangalore. He is a very good cartoonist, and he writes nice books. He has written nice popular books in gravity and black holes. And of course, he is well known for his jokes. And one of the jokes which he had, which probably I should mention here because I like it so much, is, you know, the theory of gravity was discovered not by Newton, 200 years before. Where was it discovered? In Kerala. What? Kerala. By a Nambudiri. What? How has it happened? Yes, Nambudiri was sitting under a tree and contemplating, like Newton. Something fell, apple fell for Newton. Unfortunately for our Nambudiri, a coconut fell. So he died. Before he could write, he perished. This was the first case of perish before publish. So this is the way in which people do talk about in physics, and people do create a lot of statements. And my friend Murugan, whom I know, he always talked about Mayam Suringi Vittadu, and again. Suddenly I thought, is he talking about Kamala Hassan? And then you say Mayam Suringi Vittadu. Then he is going to come and kill you. Of course, Mayam will Suringi in 450 million years. Don't worry about it. This is the way it happened. And whenever I started this Tamilnadu Science Forum and we were all involved, we used to go to schools. and talk about whatever we know in physics, chemistry, sciences, etc. So we asked them, what is the greatest star you know? Because I want them to look into the sky. The immediate answer was Rajinikanth. You know, there is a greatest star who has been living much more than that in which you can see. Go out in the sky, go out in the night and see what are the things. Sirius. Fantastic stars are there. Why don't you see and find out how interesting they are? How is it they came? How did they come? All those questions can be asked very interestingly. But we don't tell the students, oh, these are all more interesting questions than whatever it is. I don't have any problem with Rajinikanth, incidentally. But this is all something which we... And second thing is, we don't link up with what we read and what we practice in some ways. So in the schools, well, they teach the students, oh, we have 9 planets, Navagraham, etc., and they are happy. And once they go home and they go to some temples, oh, they say, oh, there are Navagraham. This thing is there. So I asked one of the students who is there, I went for this Navagraham, this thing, planets. Then I asked, what are the planets which are there in that place? He started with the statement. First statement was sun. Is sun a planet? I never knew that. Oh, then, oh, sorry, sir. Sun is a star, but it's not a planet. Okay, fine. Next, moon. Oh, is moon a planet? No, it is not a planet. Again, that's also over. Then they come to the real ones. Venus, Sevai, Budan, Vyaran, Valli, Sunny, which are 5. Which is fine. Okay, you have got 7 now. And what are the other 2? Rahu, Kedu. Where are they? Have you seen any astronomer or astrophysics? Anyone has seen? No. But we don't ever link up. When we say we are happy to hear Navagraham in the school syllabus, we are happy to see the Navagraham in the temples, but we don't think that they are 2 different things, which we never link up. So this is the problem when we want to understand what is being taught and what is being learnt in schools, and I think that's why our Science Forum has been trying very hard that you can actually see many of them. It requires, in fact, if many of students are there, I can probably, if the library gives us permission, we can have a small workshop to build a 2-inch telescope. It doesn't require much effort. What you require is the powder boxes, and then you will require few lenses which are available in any of these shops here, and you can make the thing and you can see the Saturn. Beautiful rings of Saturn or moons, crater, etc. But we never tell the students that these are possible. Okay, so now I'm going to, after this thing, I'm going into the question of what is Hawking. What is it he has done? Now, is extraordinary physics. So first I'm going to show a movie clipping which is a trailer. This is a fantastic movie which came about the life of Hawking. Can you play? Oh, no, play the before. No, go back. Go to that movie, Theory of... you have to... No, don't go to the next slide. It will come. This is a trailer of this movie which is called Theory of Everything. Is it coming? It is coming. Global trailer. So, this is...
Come on, get up. Morning, Brian. Stephen, are you aware that you voluntarily embarked upon a PhD in physics? Hello.
Hello.
Science.
That is his wife. This is it. He was declared by the doctors when he was a graduate student. 23 or 24 was his age. He will survive for 2 years. So by 26, maybe 30, he should have died. No, he lived up to 75. That lady is Jane, married, and they actually had children also. And 75 was his age. And his determination that to do something and claim some of the greatest physicists they were wrong. He was prepared to say to the greatest physicists in Cambridge and Oxford that they are wrong. In fact, when he computed something, he said you are going to get infinity there, divergent. And that worked out correctly. So this was his greatness, and I always was impressed by his determination to survive. I have seen very few people like that, who have fought against all odds. I have seen some cancer people who had cancer and suffered all these things, etc. Okay, so now I'm going to talk about what is it he has done. My job was reduced to some extent by Murugan to talk about this, but I'm going to elaborate a little more. So the little more is, I told you the part, any object will go in a straight line. Okay. But if I tell you what is a straight line from here to here, okay, any point here to here is the shortest distance from here to here. Supposing I ask you to go from that place to that corner, you will take the shortest path. Of course, there are tables here. But if the tables are not there, you will take the shortest path. So that is common sense. As he was objecting to common sense, that's what we will do. We will take the shortest path. So you can ask the question, what is the shortest path for Earth around the Sun? So that is where Einstein came into the picture. Einstein said, our space is like a rubber sheet. Just imagine the rubber sheet. In the rubber sheet, if you have a coin or marble, it will go straight line. It will go like this. Okay? Now, in this rubber sheet, I put the sun in the middle. So it is going to bend like this. It is going to become a parabolic surface, a curved surface like that. Now, if I put a marble around it, it will go around and round and round. Okay, you might have seen this kind of a video which has been shown in the thing. So what it does is, it takes the shortest path, which you can call as a straight line. That's what it is doing. It is supposed to do the shortest path. In mathematics or physics terms, we will say geodesic. That's a name. But what it says is, from here to here, what is the shortest path? But if the space is curved, as he was pointing out, it will go in a curved path from our perspective. So that's what is happening for all the things. This is the most interesting thing. But even though it looks very simple, this concept of take the shortest path, but the shortest path is curved, because the space itself is curved, is he has changed the burden from gravity, which is force between two massive objects, to say the space is curved. So nothing is happening. Mass is bringing the curvature. It curves the space. Once it curves the space, Earth knows only about how to go in a straight line. The straight line is shortest path between one point to another point. That's what is happening. So this is a brilliant idea. In 1915, Einstein brought the space-time is curved space, and the curvature is given by the presence of objects like sun, earth, moon, or any other objects. So the curvature, the space becomes curved, is the thing which is responsible for the path to look like a curved path. So this is what is happening, and this is what he was trying to tell. So in this context, what is the black hole? It is, as he pointed out, final stage of most of the stars. Most of the stars. Some of them are like white dwarfs. As he said, they are not black holes. Some of them are neutron stars. At the end, death, when its death occurs, it is neutron star or this thing. But actually he missed a little more. I will tell you what are those things. From where even light, you have a star, sun. The characteristic of a star is to emit light. It emits light because it produces energy by nuclear fusion, which he explained, and the light is coming out. And you are getting the light. here, because sun is emitting the light and you are getting it here. And what happens? Even the light it emits cannot come out. It is like this thing, you stay on earth, you take a stone, throw it. When you throw it, it comes back. Okay? Now you throw it so fast, when you throw it so fast, then if you throw, it will go to some 2 kilometers and come back. The rocket. Okay? Throw it 2 kilometers and come back. Now you throw at a speed. You throw a stone, taking here and throw it at a speed which is 12 kilometers per second. It's a very high speed. 12 kilometers per second is a huge speed. You throw it just like that. Okay? It will never come back. It will escape Earth's gravity. That velocity, that speed which I said 12 kilometers is easy to find out. Any school student, it is one of the things which is called escape velocity for Earth is 11.4 kilometers per second. If you throw it, it will escape Earth's gravity. Simple. It will not come back. Now, I want to make sure the escape velocity is the velocity of light itself. Light itself cannot escape, right? Which means, what is the speed of light? 3 lakh kilometers, everyone knows here. 3 lakh kilometers per second. It's a very high speed. Let me assure you, it's a very, very large speed. If you want to go to the moon from here, if you have a bullet train, this is a light train, okay, you will go in 2.5 seconds. That is the speed, 2 seconds, you will reach that. So that is the speed. If you want to have that as escape velocity, that means even light cannot escape from it. What should be the mass? That's the question you can ask. And that is where the black hole comes. Okay? Now the black hole idea, even light cannot escape, was given surprisingly not in this century. It was given at least 300 years before. Next slide. Okay. Why is it light? In fact, what was the greatest contribution of Einstein was light has weight, light has energy, and energy is mc square, so it has weight. If anything is mass, if anything is energy, it will be attracted by the gravity. So if you have a star here, and if you have Earth, the sun here, the star light will come straight to you. But if the sun is there, it will burn towards the Earth. So such an experiment was done. After Einstein gave this idea in 1919 by a professor called Adjunct, he went to Africa to do the experiment. How do you find you have sun and you have some star very close to that behind, okay, very close to that, and you want to see the light of the star to come to you. How will you see it? Because sun's light brightness is so much you cannot see it, right? You cannot see it, but you can see it once. That is the thing. Unfortunately, we Indians, well, some of the youngsters may have a chance. I have lost it because I cannot see it. In India, you have to see it during total solar eclipse. When you have total solar eclipse, during daytime, sun is not there. It is covered by moon. Sun is not there. It is dark, or at least in the evening. And I did go. In fact, in 1982, when the total solar eclipse happened near Hyderabad, Khammam, I did go there. 1995, it happened near Agra, Fatehpur Sikri. I did go to that place just for the 2-minute worth of pleasure. Because the total solar eclipse happens only for 2.5 minutes. So I traveled from here, Chennai, to Agra, and from there to Fatehpur Sikri, just to see the total solar eclipse, because during that time, sun is not there. You can see the stars. And when you see the stars, you can find out whether the light is bent or not. And such an experiment was done in 1919. Unfortunately, we tell our people oh, if it is total solar eclipse, don't go out. Bad radiation comes. Ultraviolet radiation comes. So, you know, in 1982, when we went to see the total solar eclipse in Tamilnadu, in all the places, Indian Airlines pilot refused to fly. At that time, Pallavan Transport Corporation declared 2 hours holiday because it is bad. It's total solar eclipse. Okay? But unfortunately, there is a fantastic astronomer from this place, Devdas was his name, Astronomy Association. He had a lot of telescopes. He made efforts, we should go and see. This is the greatest thing. He said, I will take my daughter who was pregnant at that time to that place. So this is the spirit. No big radiation comes. In fact, radiation is less because moon has stopped it. So this is what we have to tell our people, that we have to come out of such superstitions. And we did go and see, and such a thing was done in 1919 by Arthur Eddington. And the next day, the newspapers declared, after general theory of relativity, the newspapers declared 400 years of Newton's theory is thrown into the dustbin. This is the way they declared, because it is proved by experiment, and it is, you have to prove it. Physics is an experimental subject. I do theory, I do theoretical work, but we should not forget whatever speculation I have, whatever theory Einstein had, it has to be proven in experiment. It has to be seen in the lab. Even about black hole, it has to be seen. I will come to that. So, light has energy and feels the gravity. This is a cartoon. So, it has weight. So, which means it will be affected just like Earth. It will be just affected by like your stones which are falling down. Even light. For example, if I take a torch light and shine, we don't see that light is coming down like this, right? If I take a water pipe and put, the water comes down in a parabolic path, but nothing like that happens for light, because we don't see it. We cannot see it, we cannot measure it. The bending is so small, you cannot measure it. But you can measure it in extreme circumstances, and that's what was done by Eddington. Next, please. So, strange things happen. This is a well-known thing which is given to the classes, which is called twin paradox. If you go at very, very high speed, just for imagine that you can go at a speed of 100,000 kilometers, you cannot go beyond the speed of light. Okay, you cannot go beyond the speed of light. Say 100,000 or 1 lakh kilometers per second. You go at that speed. The time flows slowly for you. So there is a paradox which was created by Einstein himself. There is a twin. There are two persons, brothers. One of them took a rocket and flew at a speed of 100,000 kilometers per second and then came back. His brother, who is a twin, was there. He has become, from 20 years, 70 years, 50 years have passed, and his hands, everything is gone. And the other fellow, the young Einstein, is coming back, hale and healthy, at much younger age. Because the time flows very, very slowly if you go at very, very high speed. This is a strange phenomenon that happens because of special theory of relativity itself, and it happens general relativity also. So the next one. So this is the thing. This, I told you, this person Laplace had the concept of black hole, because he asked this question, with what velocity I should throw? With what velocity I should throw such that it escapes the gravity? So Earth you can ask. The 11 kilometers you can calculate. Any student will calculate. Now you can do that for, supposing I want that speed to be velocity of speed of light itself, 3 lakh kilometers. Then that is the speed. That's the mass it should have. So from a stellar object, just imagine you are standing there, you are having a torch light and shining the light, okay, then that light cannot go out, because even that light will be pulled back. You have to imagine, because I am asking you to do that. If the light can be pulled back, you should imagine what will happen to you, because you are also some, say 60 kilos or 70 kilos, you will be pulled back also, right? You will not, if your height is some 6 feet here on earth, you will be crushed to that level of 1 inch, because you are also being pulled by the same star. So this is the thing, and light cannot escape from that star at that stage. But this is not completely correct. Laplace's statement, that is where Einstein's work comes up, special theory of relativity and general relativity. Why? That is because, supposing the train is okay, if a train is going at 60 kilometers per second, and like that Yandiran movie, Rajinikanth is running at say 80 kilometers per hour or 100 kilometers per hour. So you can ask the question, what is the speed of the train with respect to Rajinikanth? So 100, this in 1 hour he would have gone 100 kilometers. In 1 hour the train would have gone 60 kilometers, so it's only 40 kilometers. You simply subtract. Or if you go in the other side, you will add up. So that's what is relative velocity we are teaching the students. Unfortunately, that doesn't work in special relativity. I told you strange things happen in relativity, special relativity and general relativity, because the velocity of light is same in whatever way you look at, whether you look at it from a train, you look at it from a platform, or look at it from anywhere, the velocity or speed of light is only 3 lakh kilometers per second. Nothing changes. So this cannot be simply added. But that came in 1905. That is the time Einstein gave the theory. So what is wrong with this argument is, at that time Newton's theory was working. So what if the light cannot escape with the 3 lakh kilometers, the person standing on the star, the light will not escape. What is it he has to do? He has to simply jump, because he is going to give a speed. That will be more than 3 lakh kilometers. The light speed will be more than 3 lakh kilometers. So that light can escape. But that doesn't happen in special relativity. And that is one of the crucial reasons for the existence of black holes. It will not happen in Newtonian gravity. It is very, very important. So this is the thing. The formula is correct. This formula is correct. This is what happens. But Laplace was wrong. In fact, Laplace was a great physicist, and he had this thing when he made various remarks. He said, the laws of physics tell you what will happen in future. Simply take anything. If you throw a stone, it will go and fall there. So laws of physics tell you everything. Then Napoleon asked him, where is God in this? Okay, this is the question he asked. Laplace was said, well, I don't need him. Even if he is there, he will not interfere. He will just look at it. This is what he was supposed to have said. Very interesting, but this is the way the original idea of black hole. Well, original idea of black hole is a new name which we are giving. We will realize it. This is the thing which is there. Next one. So this is the thing. It's like a hole. You drop something, nothing can come out. Hawking himself compares. It is like you are canoeing near Niagara Falls. What happens? You see, canoe is going, then falls, you don't see. That's what is happening. But actually something more is happening. Okay, next one. So the question is, how do I see the black holes? If light cannot come out, how do I see it? How do I see the black holes? What is meant by seeing it if light doesn't come out? Okay? That is a very, very important thing. And that is where the physicists' extraordinary thinking comes out. What they have is, there are binary stars. There are two stars going around each one. There are two stars going around each one. One of them is a black hole. The other one is not a black hole. So they go around each other. So the black hole is behind sometimes and in front sometimes. So you see the star appearing and disappearing as you see from here. So this is the idea which was used, and that as a concept was used and found that it is actually possible by this indirect measurement that you can see the black hole. But then physicists are not, at least astrophysics people are not simple. They will not think, how do you know? Why not it is a white dwarf? White dwarf also you don't see it so much because it doesn't emit light. Unless it emits light, you don't see it. So you have to make sure. So they find out from the period here what is the mass of the other star. You can find out the mass of sun from here because from the period itself. Right? These are brilliant ideas. We have Earth, we have Jupiter, we have Sun. From the periods, we can find out what is the mass of Earth, what is the mass of Sun. Just imagine, it's like taking a weighing machine and weighing Sun. So you can do that. You don't need the weighing machine. That's where the whole idea is coming. Said from the mass of the star and using the concepts like collapse, which he talked about, the mass is greater than 10 solar masses. The only way it can exist is as a black hole. So that is where the conclusions come. Okay? So this is the thing. What happens is you have the star and the other object is going around, which is, if it is a black hole, it just pulls anything from that side. Even the atmosphere of the other one, hydrogen, helium, etc., is being pulled by this. So there will be what they call a disk of gas pulled from here, from the other star, and that disk, name for it is called accretion disk. And that disk, because it is coming with a lot of velocity, it gives you a lot of heat, it gives you light, and the light ray in the form of X-rays come out. So they can see using X-ray telescope what is the wavelength of that X-ray. So this is some of the ways in which the black holes are seen. Now I am going to tell a little more about some of the things which is there. He talked about sun, which has one solar mass, because sun is the definition. It has to have only one solar mass, one sun mass. So there are stars, okay, which will have, as he said, Chandrasekhar studying in Presidency College, a 20-year, 19-year-old student who came to know about these things. He did this work. He went to Cambridge. While going by the ship, in those days people traveled only by ship, I'm talking about 1930s. While going by the thing, he did these calculations about white dwarf. He came to the conclusion, if the mass of the star is less than 1.4 times the solar mass, it will not collapse, it will form white dwarf. This is the conclusion which he came. And who opposed it at that time? There are two people who opposed it. We should see, we have to understand physicists are also capable of making mistakes. Who was the first one to oppose it? Arthur Eddington. And he is a giant, he is a student. He says that the star will collapse if it is more than 1.5 solar masses. And the Eddington says, no, it will not collapse. You know, he didn't get a job. You have to prove. He didn't get a job. Chandrasekhar didn't get a job in UK. In those days, US was not the famous. You had to work in Germany, you had to work in UK, etc. So he went to Chicago looking for some jobs. Of course, it had a lot of difficulties. The second person who said black holes will not be formed, as his remarks were there, was Einstein himself. Einstein himself said, stars, something will come and stop its collapse. But he didn't know what. It didn't come, he didn't know. But something will come, because the physics cannot go to that singularity. Okay? He said it cannot happen. This is what happened in those days, which was very interesting, 1940s. 1940s was extraordinary period in the history of the world. Second World War was taking. People were discovering greatest physics, chemistry, Even genetics came around that time. Fantastic works were being done. Radar came. For example, all the works which we are getting now, the developments took place in 1940s. So very interesting, but this is what happened. Einstein was opposed to that, and Eddington was opposed to that. Poor Chandrasekhar could not get recognition for his work. And I should tell you, he is not completely right. Because he said 1.5 solar masses. And it is true, most of the stars like white dwarfs in those days was less than that, and that's what happened. In the last 15 years or 10, 20 years, 15 years, a lot of white dwarfs have been found out whose masses are of the order of 2 or 3 solar masses. Where is it coming from? That's a question we are asking. In fact, I myself is working on that. Because the star which has this kind of a mass, because it has a magnetic field, that original calculation of Chandrasekhar has to be modified, and it gives you more possibility, more increased mass, such that it can form a white dwarf. Okay, that's fine. So my friend Murugan said there are 3 or 4 solar masses, 10 solar masses will give you black hole at the end stage. Now there are black holes of 100 solar masses. I don't know whether you have heard recently, last 1 year, gravitational wave detection. What happened? 2 black holes collided. What is the mass of the black holes? 35 solar masses. 2 of them merging to form 70 solar masses, and something is left out, and that produces a wave. It is like 2 stones hitting, like our Ramayana movie, 2 arrows come and hit. Like that, they were colliding and waves are created. And where does it happen? When did it happen? Now, that is also another mind-boggling. It only happened 3 billion years back. 3 billion years back, it happened, and the wave from that is coming towards us and shook our earth by 1.0000000 20 zeros you put after that 1 millimeter shaking of the earth. 20 zeros. 0.00, but people can measure it. People can measure it now. That is a kind of work that is being done. This experiment is called LIGO experiment. In fact, most interesting thing is there are at least 50 scientists from India, young people, are part of this project, including one from my institute. One from my institute is part of the same project. His name is Arun. He is there in that project. About 1,000 people collectively did this work by a lot of calculations, because this enormous amount of calculations you have to do. You have to verify. Those people are doing in US. You have to verify. And you know the kind of equipments which are there for the detection is amazing. It is in effectively Bundak's place. Totally unpopulated desert area. Some road is there about 4 kilometers away. If a car goes there in that 4 kilometers away, this instrument will show slight shake. So they have to avoid such shaking also. You should not have. They are all disturbances. You don't want that as a gravitational wave. Gravitational wave has to come from 4 billion years back. Just imagine how far is it. So this is the kind of work which was done, and this is what is happening. Now I'm going to shock you. There are black holes which we don't know. We have an idea about the black holes which Murugan talked about. Stellar evolution, 3 or 4 solar masses, 10 solar masses. We don't know even about 30 solar masses. How do they form? How do they get that kind of mass? There is a black hole at the center of our galaxy, at the center of Milky Way galaxy. What is its mass? Million solar masses. It is million solar masses. That's a huge object. It's huge in the sense of mass, but in terms of the size, it's 30 kilometer size. It is only 30 kilometer size, because you are having million solar mass sun packed in a volume of 30 kilometer radius. Just imagine that. You have million suns packed in 30 kilometer radius. We don't know how they get that kind of thing. There are so many of them. In the center of each and every galaxy, there is a black hole like that, which is called supermassive black hole. We don't know how they come. One of the theories, see, I am very old. I am retired. I am looking for young people here, like Chandrasekhar at the age of 19, 20, come with brilliant ideas, come with fantastic ideas, read them, speculate, compute, verify, check, talk to people, and give a theory for how such a supermassive black hole can be formed. We don't know. I tell you, we don't know, period. There were several theories, including Hawking himself had some theories, which is wrong. Okay? So, when the black hole, such a thing was discovered, well, when they were looking for discovery, they were looking for candidates. Where is the black hole? There is one candidate, they said, Cygnus X1. There is a star constellation called Cygnus. In that X1, they found some possible example of a black hole. And of course, Hawking didn't believe it. What did he do? He went on, probably next one. Okay, so we don't know whether the binary which is there is white dwarfs or neutron stars. We have to verify whether it is there or not. Cygnus X1 led to a bet between Stephen Hawking and Kip Thorne. Kip Thorne, well, he mentioned it. He was also famous for the movie Interstellar. He was the scientific advisor for that movie. He was the scientific advisor for the movie where somebody goes through the black hole, through something, and then come out through the Saturn somewhere. Okay? So this is the kind of a movie which is interesting. If you have not seen, please go and, well, I'm not advertising for anyone. So this is the thing. Of course, he had a bet, and he said that Cygnus X1 is not a black hole in 1974 or 5, and they had a bet for several years, and people are now convinced, including Hawking himself, that it is a black hole. So he lost his bet. So this is not the first time. Hawking has a habit to, in order to invigorate himself, he gets into a bet with several people, and I have not come across a situation where he won. All the time he lost. He was very happy about it. So this is the accretion disk from where X-rays are coming, and for all the students I will tell you, there is a satellite, this thing, observatory, which is called Chandra Observatory. They have kept an observatory in honor of a physicist from Chennai, Chandra. There is an observatory, X-ray observatory, which is observing. There is a fantastic website. You can go to that website, you can click there, I want to see this constellation. That picture will come. And they will even turn a program in such a way that observe the telescope, because it's a telescope, towards some direction which you find it interesting. So this is a thing which you should know. The next one. So gravity and quantum theory, there are two of them. That's where Hawking comes into the picture. And 10 minutes? Okay. 20. Okay, good, thanks. Gravity was given, the general relativity was given by Einstein, 1905, 1915. 15 was the general relativity he gave. And quantum theory came in 1901 from Planck, Max Planck, and then developed into full-fledged theory by 1925. This is the status of physics in that period, and this period is a revolutionary period for physics. In fact, there is a book called 30 Years That Shook Physics, and this is that period. And unfortunately, the gravity theory and quantum theory don't agree. They contradict each other. They don't agree at all. There is a problem. If you use a quantum theory, you are getting wrong results. If you don't use the quantum theory and do your conventional general relativity, you see everything nicely coming out. So that is the beauty of this thing. So Hawking comes in 1970, around 1964 he got his degree, 1970. Now the earlier name for the black hole was not black hole. It was called frozen star. A star which has frozen because nothing comes out. Okay? It is frozen star, but Archibald Wheeler was the person who called it black hole in space-time. He said there is a hole in the space-time. So anything goes there, like for example in the hole in the streets here, which is we are very familiar with. Chennai streets have a lot of holes. You fall into that, you don't come out. Okay, that's a kind of a thing. And he gave the name black holes. If black holes can only absorb, what is it can do? It can only absorb. It cannot let out anything. Then its mass can only increase. Its mass can only increase. Its volume can increase. Area can increase. The only thing it can do is increase. That this is not the only thing. We know that something happens in one direction. We know in heat, from hot object you can go to cold object. Heat goes one thing. Have you ever seen cold object giving heat to the hot thing? It cannot happen. So that is what in physics we call as a thermodynamics. We call it laws of thermodynamics. Heat can go only from hot to cold, and there are three laws which are there, which is any textbook will give you, undergraduate students do learn, and all are saying the same thing in different ways. They will say an engine, heat engine cannot have an efficiency of 1. Okay? It has to be less than 1. It is like thing, if I give 100 rupees to be given to somebody there, through this process, he will not get 100. Somebody will take in between. Right? So that is the thing. Heat engines cannot be an efficiency of 1. Or hot to cold heat is possible, cold to hot is impossible. It's almost like mass can never decrease, it can only increase. Area can only increase. So this is what people call as the laws of black hole thermodynamics. They call it laws of black hole thermodynamics. And when you have thermodynamics like that, there is some quantity which people called entropy. So every hot object in equilibrium will have what is called entropy. So that entropy can be assigned to the black hole also, and that was what was done by 1974 with my friend Sriram's. He worked with Bekenstein, right? So Bekenstein was a person who worked in Israel, and he actually gave this law, black hole thermodynamic laws. He was the person who gave those laws, and at that time he said that entropy is same as the area. Entropy is same as area. Area can only increase. Entropy can only increase. Heat can go only from hot to cold. All those things are all equivalent statements given in different ways. So this is the thing which was there. Now we know there is a deep connection between thermodynamics and black holes. But there is no quantum theory. That's where Hawking comes. He said, if it is a hot object, I know hot objects radiate. Right? There is a hot object, it radiates. Why can't a black hole radiate? He asked that question and said, if I use minimal quantum theory, he didn't use a full quantum theory, the minimal quantum theory, black holes do radiate. Now if they don't radiate, now you have a black hole, I have a chair here, I throw the chair, what will happen to that? Chair will be eaten. The chair has lot of details, right? It has lot of details. The information about the chair is lost completely. The information about the chair is lost. So what we know about black hole is there are only 2 or 3 numbers you have to give. What is its mass? What is its angular momentum? How fast it is rotating? And what is its charge? Charge of that black hole. These are the only things that are required. There is a name for it. In fact, next my video will show this thing that is a sort of, when people call it as black holes, they started calling it as sexy. And they went one step ahead, because these people went and said, okay, the black holes don't have hair, because there is no other information. There are only 3 information. So this is what happened, but anyhow, we mean that black holes do not have information other than mass, angular momentum, and charge. So this is a thing which was brought down by Hawking by claiming black holes do radiate. They also give out radiation, because like any hot object will do that by forming using certain quantum theory. Essentially, the electron-positron pairs will be formed near that horizon which he mentioned, what they call the horizon, the surface of the black hole effectively, and one of them will be pulled, the other one will be gone. So that will give you that information if something is going out or not. So this is the major contribution of Hawking in 1974, when I started doing my research as a graduate student. I started learning what is quantum theory, what is general relativity, etc. At that time, this is the thing he gave, that black holes do radiate. It is not dull object like something which is the Calcutta black hole where people were put as prisoners and nothing is seen, like that. So this is what happened. Next one. So, and peculiarities is, as my friend mentioned, where the surface where light cannot come out, it is called event horizon. Going through that is a one-way traffic. If you are having that event horizon black hole, if you are going through that, it's a one-way traffic. You cannot come out. Unlike Chennai traffic, there are one-way streets where people do come on the other side. But this is law of nature. It is not law made by our people here. So law of nature tells you, if you go through, no, you are not going to come out. Okay, that is what is there. So if you fall through, this is also funny. If you fall through, say with your legs first and head later, your legs will feel greater gravitational pull than the head, because it is closer to the black hole. So your leg will be pulled. So you will become stretched like a spaghetti. He called it a spaghetti, and that's what will happen, like noodles. And this is a kind of a thing. So if you really want to see what is happening inside the black hole, you should never attempt to go near a solar mass kind of black holes, 3 solar mass, because there the difference is quite high. The force between leg and the head is so different that you will be torn into pieces. But if you really want to see where nothing happens to you, within quotes, is you should go near a supermassive black hole. If it is 10 power 6 million, that million solar mass, if the force of gravity is so much, the distinction between the distance, leg and the head, is so little that you will have the same force in your leg as well as head, which means you will go through nicely without feeling anything. Okay, that's what, in fact, this idea was given by Hawking himself. This way of describing was given by Hawking himself. So, Hawking's advice, if you want to go inside a black hole in one piece, choose a supermassive black hole. Go to the center of the galaxy, and Sagittarius is the name for that black hole, and you go inside. That's it. You will not notice anything strange as you fall through it, because the whole body is going. Okay, you will not find anything strange. But as we told you, the time goes slowly for a different person, because he is not going with that kind of speeds. So if a distant observer is there, this object which is going inside the black hole, let us say he is emitting light, shedding light. That light will take a lot of time to come to you. If he is sending something like the yellow light or green light, it will become red and red and red, and you will not find that it looks as though the person, information that the person is going inside the black hole will take more time to come, because it will almost stationary on the surface of the event horizon for a long time, for a very, very long time of the millions of years. So this is the beauty for a person who is far away, and the person who is, or the information is going in, like thing, the information takes a lot of time to come because of this famous effect which is called dilation. Time is changing. Time is changed. So, but a distant person observing, you will keep seeing you all the time as though nothing has happened. You are sitting on the, so it is like this canoe is going towards the Niagara and almost at the edge. It doesn't fall. You will see it all the time there. That's what will happen. This is what general theory of relativity tells you. Next one. Black holes have no information except mass, angular momentum and charge. What inside, went inside, everything is lost. Whatever is made up of chair, table, other stars, everything which has eaten it, nothing, no information is available, and this problem is called information paradox. So there are some works which have happened, and this entropy relation was worked out by his advisor or postdoctoral advisor along with Hawking, which is now called Bekenstein-Hawking formula, which I have written S is equal to A by 4 in some units. You have to see what it is, and this is what is the result. So this is a very new situation, a paradoxical situation, that radiation can come out of it and we can also see it from that information. So this is the thing, but only thing is it looks like information about the details of the information seems to be lost. So this is one of the outstanding questions in physics. Is information lost or can we get the information? That is one of the things which people call as information loss paradox. Next one. Okay. This is actually a video. I thought about giving this video. This is the last one. I thought about giving this video because of one reason. You should hear Hawking. Okay? This is a lecture which he gave for BBC. It was actually given in Chile, and it explains what is the thing. It actually, there are 4 parts to it. I've only taken a 10-minute part of it, and that is what is there. Can you play the video? No, play before. What? It will come actually. No, go before. No, it takes time.
Well, right now, physics is the main course, so serve it up if you would, Stephen. Ladies and gentlemen, lecture number 1 is entitled, Do Black Holes Have No Hair?
My talk is on black holes. It is said that fact is sometimes stranger than fiction, and nowhere is that more true than in the case of black holes. Black holes are stranger than anything dreamed of by science fiction writers, but they are firmly matters of science fact. The scientific community was slow to realize that massive stars could collapse in on themselves, under their own gravity, and how the object left behind would behave. Albert Einstein even wrote a paper in 1939 claiming stars could not collapse under gravity because matter could not be compressed beyond a certain point. Many scientists shared Einstein's gut feeling. The principal exception was the American scientist John Wheeler, who in many ways is the hero of the black hole story. In his work in the 1950s and 60s, he emphasized that many stars would eventually collapse and the problems that posed for theoretical physics. He also foresaw many of the properties of the objects which collapsed stars become, that is, black holes. During most of the life of a normal star, over many billions of years, it will support itself against its own gravity by thermal pressure caused by nuclear processes, which convert hydrogen into helium. Eventually, however, the star will exhaust its nuclear fuel. The star will contract. In some cases, it may be able to support itself as a white dwarf star. However, Subramanian Chandra's expert showed in 1930 that the maximum mass of a white dwarf star is about 1.4 times that of the Sun. A similar maximum mass was calculated by Soviet physicist Lev Landau for a star made entirely of neutrons. What would be the fate of those countless stars with greater mass than the white dwarf or neutron star when they had exhausted nuclear fuel? The problem was investigated by Robert Oppenheimer, of later atom bomb fame. In a couple of papers in 1939, with George Vodkoff and Hartland Snyder, he showed that such a star could not be supported by pressure, and that if one neglected pressure, a uniform spherically systematic symmetric star would contract to a single point of infinite density. Such a point is called a singularity. All our theories of space are formulated on the assumption that space-time is smooth and nearly flat, so they break down at the singularity, where the curvature of space-time is infinite.